In this video, we are going to be learning about titrations. This will support our learning objective for applying stoichiometric relationships to calculate amounts of substances involved in chemical reactions. So what is a titration? Well, a titration is used to analyze the precise quantity of one solution using another solution. So like your titrant here would contain this is a burette, and the burette would contain a solution that you know the concentration of. You will record the initial volume and then you'll record the final volume in order to figure out how much you added. Then you'll be able to calculate the number of moles you've added to your analyte. Your analyte is what you're analyzing. This you do not know the concentration of. But you have added an indicator which changes color at a specific pH to give you a visual clue about when you're done with this titration. You're done when you reach the equivalence point. The equivalence point is, well, your goal is to be done at the equivalence point. You'll really end at the end point, but the equivalence point is where you're exactly on stoichiometry, meaning there's nothing in excess and both reactants run out at exactly the same time. The end point is where the indicator changes color to let you know that you've reached there. But the indicator should be picked such that the endpoint is really, really close to the equivalence point. There are a variety of indicators, as shown here, that change color at different pHs. And so, for instance, phenolphthalein changes color from clear to very light pink around pH 8, which is slightly above pH 7, which is the neutral. So in this region, it's really, really faint pink, and that's the endpoint. And then there's other indicators that also undergo a color change at different pHs, so that you can select an indicator that changes around the correct pH for your particular reaction. To make math easier, we're going to assume that the end point is at the equivalence point, but it isn't really. So here's an example of the type of math that's possible using a titration. This one says a 0.4324 gram sample contains a mixture of potassium hydroxide and lithium hydroxide. This sample requires 28.28 milliliters of 0.3520 molar HCl to reach the equivalence point. What mass of lithium hydroxide is in the original mixture? So this is a mixture of KOH and lithium hydroxide. So we'll write that up here. So 0.4324 grams is going to be equal to my mass of potassium hydroxide plus my mass of lithium hydroxide. And then we can use this number to calculate our moles of HCl from that. HCl will react with lithium hydroxide in an acid-base neutralization reaction to form lithium chloride and water. HCl also reacts with potassium hydroxide to produce potassium chloride and H2O. Both of these are strong bases, and that HCl is a strong acid. You'll notice that in both of these reactions, it's a 1-to-1 molar ratio between the acid and the base. And that means no matter which base the HCl is reacting with, it's a 1-to-1 molar ratio. So that if we do calculate our moles of base, we know that that's the total moles of base. So let's go ahead and do that. Let's convert this into liters properly. So I converted my milliliters into liters, and then this is of HCl, And then I'll cancel out my liters of HCl solution and get into moles of HCl by multiplying by the molarity. And then from my stoichiometry, I know that I have 1 mole of HCl for every 1 mole of base. I don't know which base it is, but I do know it's 1 mole of base. And so this is 0.02828 times 0.3520. I'm going to write this down. 0.0099545 moles. And I'm going to go ahead and store this. To make sure that I can keep that number. Okay, so this tells us that the moles of potassium hydroxide plus the moles of lithium hydroxide is equal to 0.0099545 moles. So now we know what the masses add up to, and we know what the moles add up to. So if we take this original equation here, we have 0.4324 grams, and we're interested in solving for the mass of lithium hydroxide. And so that means wherever I have this mass of potassium hydroxide, I'm going to try to get rid of where it says the mass of potassium hydroxide. I know that I can get the mass of potassium hydroxide by taking the moles of potassium hydroxide and converting that from moles into grams using the molar mass. And so that is the molar mass of potassium hydroxide is 56.107. So I can take my mass of lithium hydroxide, and instead of writing mass of potassium hydroxide, I can instead write moles of potassium hydroxide times the molar mass of 56.107 grams per mole. Now that might not seem like it helps us very much, but it does, because now we're one step closer to getting rid of this moles of potassium hydroxide using this molar relationship. I rewrote some things to give us a little bit more room. Now that we have our moles of potassium hydroxide here, we can take this previous equation and we can solve for moles of potassium hydroxide by subtracting mass of, this is moles of lithium hydroxide from both sides. And so that tells us that moles of potassium hydroxide is equal to this number minus moles of lithium hydroxide. So now we can plug that in where we see our moles of potassium hydroxide. And so that's 0.009856. I stored that number in my calculator. And that's moles. And then we're subtracting out moles of lithium hydroxide. Then we can solve for moles of lithium hydroxide in terms of the mass of lithium hydroxide by using the molar mass. So our moles of lithium hydroxide are going to be equal to my mass of lithium hydroxide times inverse of the molar mass. So I can cancel out the grams and be left with moles. Okay, so now we'll plug this in there. And so we have 0.4324 grams is equal to my mass of lithium hydroxide. I'm going to leave off the units for now to make it look more like a straight up math problem. Okay, so that's my mass of lithium hydroxide. So now I need to distribute this out. And so we have 56.107 times my value that I stored. And so that will give us 0.4324 grams is equal to my mass of lithium hydroxide plus 0.5585 minus 56.107 divided by 23.947. And so that is 2.3429. Okay, so now we're going to combine like terms that else had my mass of lithium hydroxide multiplied by it. So our like terms are these two terms, and then we're going to have that and that bonded together. So I need to subtract the 0.43 and erase some of this. I have a little bit more room. Hold on. And so I'm combining the like terms. So I have my mass of lithium hydroxide and so this is just going to be equal to negative 1.34296 mass of lithium hydroxide. I got to figure out what that is. And so okay, so we have 0.4324, and if I go through my history, I can find the previous value. Didn't let me save. Okay. So we have 0.4324 minus, will it be my previous answer now? No. Fine, I'll retype it. 0.4324 minus 0.55825. And so that is negative 0.12585. then I can divide both sides by this coefficient in order to cancel that out and solve for my mass of lithium hydroxide. So we divide that by, where's my negative sign? Nope. Divide by negative 1.34296. And that gives us a mass of that. To enter first before I divide. Okay, so got that number, and now I can divide. If you don't communicate with your calculator, you get weird results. There we go. So my mass of lithium hydroxide is equal to 0.09371 grams. And I need 4 sig figs. 1, 2, 3, 4. So there we go. Here's a practice problem for you to solve. Go ahead and pause the video and try to work this one out on your own. It's not as complicated as the past example. Unpause the video when you're ready to check your work. Okay, let's go ahead and get started. So we're given a volume of sodium hydroxide, and we're given its molarity, which is going to be a conversion factor to get into moles of sodium hydroxide. And we're titrating the sulfuric acid, and we're asked to find the molarity. I know that molarity is equal to moles over liters of solution. So my liters is going to be that 15 milliliters, and I'm going to have to find my moles of sulfuric acid. That way I can calculate the molarity. So if I take my 31.86 milliliters of sodium hydroxide and I multiply that by the molarity of the sodium hydroxide, I can find my millimoles of sodium hydroxide. I'm intentionally leaving this M here. It will make a little bit more sense in just a moment. But canceling out my L's, and now I have millimoles of sodium hydroxide. Now I can cancel out my moles of sodium hydroxide and get into moles of sulfuric acid. But really I'm in millimoles of sulfuric acid. And so 31.86 times 0.2037 divided by 2 is equal to 3.2449 millimoles of H2SO4. So my molarity is equal to 3.2449 millimoles divided by 15.00 milliliters. Now the millis cancel out, and then I'm left with moles per liter. So I have to take this number and divide by 15, which is 0.21632 molar H2SO4. There we go.